Good morning, everyone. My name is Faisal Otebi, and today I'll be talking about MATLAB as a calculator and operation with vectors and matrices. Simple arithmetic can be used in MATLAB with proper symbols for each operation, just like a calculator. For example, you can use a function such as the multiplication when you use symbols such as this one, the asterisk. The direct operation will be stored in the variable ans. Also, other operations such as the square root or cosine, sine, and the rest of the operation can be used also in the MATLAB. I found these examples. For example, the direct product of 17 times 459 sine of the 375.48 and square root of 9,343 also can be calculated with the proper symbol of the operation. As I said, if you want this to be stored in a certain variable, you can name that. Otherwise, it will be stored under the ANS, which is short of answer. If you don't desire the calculation to be shown in the MATLAB, you can end your statement with a semicolon. That way, it will show only the answer. We have different ways to create a variable. We can name a variable that would be a number or a simple letter. Then we follow that by the equals to symbol. And this we can name whatever variable we need. For example, if we name the variable a to equal 3.14, that is pi, or for example, also b equals 9 divided by 4. Same way, we can operate different mathematical operation on these variables. We can find the direct summation, we can find the direct multiplication, and we can divide them, or also we can find sine or cosine functions for each variable, as shown here in the example. We can create matrix on MATLAB. We have two different ways to do that. The first way is we would do it similarly the way we do it on a piece of paper. We use for that spaces that is shown in the left side of the example. Also, we can do a different way. We can make it, we can type it in a linear fashion, but we can divide each rows by a semicolon. That way we can make matrices with two different ways. We can do an operation on these matrices. For example, you will start typing the operation on the name that you give it to the matrix. For example, the matrix A from the previous example, if we add the number 10 to each row and each column, we will get the product stored in the ANS similarly to the previous ones. Also, we can get, for example, the sine operation for matrix B. This way we'll have each value as a sign for each column and each row. And that's what I have, and I'm be happy to answer any question.
Any questions in the class? Any questions online? If you have a row vector, how to make it a column vector?
You mean how to switch columns to
rows? Yes. How to transpose matrix?
You use the -1 simple.
In MATLAB, not inverse matrix, but transpose. Here is the help from the class.
Yeah, just to add a prime.
Yes.
Yeah.
Okay. Yeah. Thank you.
Yeah, I meant that. Yeah.
Hey, more questions to Faiz? 1, 2, 3. If no, let's thank Faiz once again.
You're welcome.
Faiz, please stop sharing.
Okay.
And next presenter is Tyler Clark, right? Right. So Tyler, please consider to start sharing screen.
Okay. All right. Oops. One second. All right. I did functions, derivatives, and graphics in MATLAB, and first we'll go over functions. Basics of functions in MATLAB is how to do how to do them is you gotta declare a function name, write the input, the output, and end it. This is an example of a function. In the script window, you create a new script. And the first line you write function because to describe it's a function, and I put f as the output name. You can put any kind of name you want. In the parentheses x, I made the input pretty much a variable, and I named the function make a square, which you can name anything you want. In line 2, you write the function that you want to do. Like in this case, I called f from output equals x squared, x being the input, and gets you f will be the new output it gives. And then line 3, you press end, you write end, and once you do that, you save the function and it'll come out to make a square dot m. And in the command window, you write the function name, in this case make a square, in parentheses write the variable for the input, because x squared 3 will make 9, and that's your new output. It wouldn't work for me when I tried it myself, so hopefully it works if someone else tries it. Next is derivatives. Basics of derivatives is you gotta create a symbolic expression, create a function, and then you can take the derivative of it, the function. And there's other types of derivatives that can be done too. The simple derivatives, regular derivatives, you just SYMS x. That's symbolic expression calling x out pretty much. The first function I wrote is f equals f times x, and then I pretty much just the derivative of function f, but diff, and I got the answer of 5. It also can be done with more complicated versions with cosine or even multiple versions of it too. This is a simple which works pretty well. So, and you can do it with multiple functions like I did with g and h, and still works fine as long as you put them in the parentheses correctly. More complicated versions of derivatives is taking the second derivative, in this case h, just do regular derivatives, diff of h, get the answer out. But if you want the second derivative instead, you just do diff of h, comma 2, and that's the second derivative. As partial derivatives is similar to how just regular derivatives, but instead of just one variable, you do two variables, and whatever function you want. But in this case, instead of when taking the derivative, you do f comma x. So it's partial derivative to x, not y, and you get your answer out of that going to x. And you can do the same thing with taking partial derivative. In this case, it's same as previous one, but diff f comma x comma 2. In this case, the answer is 0 because that's how it was this time. Some graphics in MATLAB is with line plots, 2D and 3D, and some 3D plots of mesh, surface, and contour, the ones I chose. Line plots is with 2D versions, this upper right corner. That I have x equal to line space, and then in parentheses how much you want. Like I did -10 to 20, as long you can see along this line plot, and I made the y function x divided by x squared plus 5, and that gets what you see on the screen as after you plot x and y. And plotting a 3D line plot is similar to the 2D, but you just add the z-axis, similar to how you did with the x. In this case, but the difference is you do plot 3 x, y, and z, not just x and y, and it gets you something like this. It's something linear because I did y equals 5x in this case. So these are some 3D plots, mesh, surface, and contour plot. They're all pretty much similar on how to make them, starting with peaks. I did peaks of 50, or z equals peaks of 50. Then you write the right figure. Then for mesh of z, and then surface of z, and then contour z 28. And that is pretty much it for me.
Okay, let's thank Tyler. Any questions in class? Any confusions? Any questions online? I have a little, it's not confusion, but a comment. So it would be natural to have a confusion while listening to Clark, because in the labs we did finite differentiation in numeric format, and Tyler taught us how to do how to use symbolic package, which is cool for some academic problems which one can get in undergraduate things when functions are defined well. But if there is something novel, there are frequent chances when functions cannot be expressed in like science or cosine, and can be represented only in numeric form. So no questions. Perfect presentation. Let's thank Tyler once again. Xin Yang San is the next speaker. So please mount it to your probably just
But how can I control the slides? Okay. Which one? Okay. Can you hear me? Okay. Good morning, everyone. My topic is saving and loading. Saving and loading files. First, we after finishing the writing the program. Sorry, can I use the program, and we run it and make sure the data and the figure both are all right. So we add a new editor, and we copy and paste all the effective program into the editor, and we then we save it as a new we save it as a new MATLAB code files. Here I named it save and load files. Then we save it. Next, we for the data, if we want to save the data, we just put save space minus ASC double I. My data 3. Here I named the data is my data 3. The my data 3 in the comment window should be exactly same with the save with the editor windows. So after this is a document is created in the file. How to find the document? We just put a pwd and then enter. The path will be showed like this, like the answers. And then using the path, we could find the document, this document. And we could open the document in the text format, like this one. If we want to save the if we want to save the data in the Excel, we just click the data and from text or CSV, and we find the document, and here we pay attention to the all files. So the document will be shown in this window, and we just input the document, and then we go to this window. For the file origin, we choose the Central European windows. For the delimiter, we choose the custom, and the data type detection, we choose the based on entire data set. Then we load the data. So the data will be transformed into the Excel, and then we save the Excel. As for the loading files, we just put the new data equals load my data 3 here. My data 3 is the data name, and then we put another new data, enter. Then we got the new data like this. That's all. Thank you.
Okay. Any questions in the class? Any questions online? Okay, let's thank Shinya once again. Thank you. And now let me invite to the virtual stage Chameli Samara Vikrama. Please correct me if I didn't pronounce your name.
It's right.
Okay.
It's correct.
Okay, thank you.
Shall I share? No, wait. Share my screen?
Yes, share my screen.
Can you see?
Just a second.
Yep, we can see it.
Oh, yes, thank you. This way.
Can you see?
Yes.
Okay. So for so for this project, we use MATLAB and script as our instrument. And the objective of this project is to learn how to use MATLAB, for running script for an icing model with coding. So my topic for today's presentation is input parameters. So input parameters define and differentiate functions, and also setting up parameters and structure includes vectors that define atoms and also the number of atoms in one unit. So we can see a simple picture on the next slide. Here, the vectors and the bond length are shown in a simple picture of a unit. So there are 2 atoms per unit here. And also these are some basic input parameters I listed. Cell size, spin-spin coupling, which is indicated by J, and also the magnetic field, which is indicated by B. So let's look at the script now and how this input parameters are entered in MATLAB. So these are the main parameters. You can see B is the magnetic field, mu is the ferromagnetic ratio, and magnetic moment of spin. So J is the most important input parameter here. So it is indicated, it is set to a negative value here. So J indicates coupling between near spins. KBT is the Boltzmann constant into temperature. So the temperature is selected in terms of room temperature and conversion factor. So this is the conversion factor, 27.2. So for my section, these are the main parameters to focus on, but I will quickly go through a couple of other parameters in the next few slides. So this bond, this is the length, the bond length between 2 ruthenium atoms. It's entered in like angstrom. Next, from line 19 to 22, we are not going to change these, but these are used as variables in the code. The line 99, it is the scan of temperatures. So the temperature is selected in the range of 0 to 6 times room temperature. So for example, if we have 300 Kelvin as room temperature, the range would be 0 to 300 into 6, which means 0 to 1800 Kelvin. So this is the last input parameter for me. It's the number of microstates. So here it is set to 20,000, but we can always lower this number. Like if we set it to like several hundred, the results would be inaccurate, like imprecise, but we can run the program really fast if we lower this number. Finally, so this is the same as the same as previous slide, the number of microstates. So I just wanted to include the results obtained upon running the whole code in MATLAB. So this graph, it indicates that the computation worked successfully. So I think that's all for my presentation today.
Thank you.
Thank you so much for attention.
Thank you. It's really helpful for us towards the project. So any questions in the class? So it was crystal clear, right? Any questions online? If no, let's thank CHEM759 once again.
Thank you.
Thank you. In the future, we will try to practice more questions, but now I think we are doing really well with timing. So, Chema, please stop sharing.
Okay.
And the next presenter will be Kim So-hee.
Thank you. Hello everyone. So from the Tamil, I will continue on about the periodic boundaries and Ising Hamiltonian. So this is the result that I got from my part of project. So this means that, as Tamil mentioned, each of those okay, each of these are the atoms. And from here, I want to mention how the numbers comes from. So the bond is 3.6 Armstrong, which means from here to here, the bond length is 3.6, and the unit is okay. So unit is like this one cell, and if so, unit is bond times square 3. And if you want to know where is the square 3 comes from, I will let you know in person. It takes forever. And the A is this axis, and B is this axis. So A is horizontal, so it is not tilted. So A is just a unit in zero matrix, and this is a translation unit vector of A direction. But B is a little bit tilted. So to express the B direction, you need to use the unit times 0.5 and unit times square 3/2, which is this 0.5 comes from cosine 60 degrees, and this vertical part is sine 60 degrees. So you can express the B direction. And atom 1 is a third of A and a third of B length, and the atom 2 is a 2/3 of A and 2/3 of B. And Na4 means that we can see 1, 2, 3, 4 units of the A direction and 1, 2, 3, 4 units of B direction. So K max is coming from these two on each unit, and 1, 2, 3, 4 of A direction, 1, 2, 3, 4 of B direction. So totally the number of unit is 2 times 4 times 4. I think I did something wrong. Can you click? Thank you. And this is mentioned in the last class. So this is original atoms, then original atoms and next to 3 atoms. And I think this is much better to explain that. So here, I'm gonna give you 2 examples. For example, one here is the original atom. Let's say this one is A11, and which atom is close to 3 neighbors, which is B21, B11, B12. And you can see with the Ising Hamiltonian table that A11 is close to B11, B12, and B21, but not B22. And this J means that spin-spin interaction, the constant, and also B21 is next to A22, A21, A11, and you can see B21 is next to A11, and it has a spin-spin interaction with A11. A11, A21, and A22, but not A12. And from column 82 to 96 is, to be honest, I'm not sure that's right, if I did right, but this is about the matrix of interaction of the neighbors, and it shows this big graph, and it shows the units of the unit. But yeah, this is done from my presentation. Thank you. I tried to explain like a lot of information that I know.
Don't disappear. There's a chance that there will be questions. Any questions? So you do not want to give your classmates hard time. Yeah. So okay. No, it's really good talk. So here it shows like zeros. Maybe one needs to adjust the z-axis to see them better. Yep. Yep. But really great presentation of Ising Hamiltonian. Any questions online? Questions 1, questions 2, questions 3. Let's thank Sophie once again. So next presenter is Ivan Pavici, if I pronounce well. So Kevin, please consider to share screen.
Hello everyone, can you hear me?
Yes, we can hear and see you.
That's great. But I think I cannot share my screen.
Okay, let me fix it. Damon, co-host. No, you are co-host.
Okay, let me see.
I think you need to stop the sharing on your side. There you go.
Okay, let's try once again.
Yes, that's it. Let me share. Okay, I think you're able to see it right now, right?
Yes.
Okay, that's great. All right. Hello everyone. In this part, I'm going to explain part 6 about assigning microstates and how to visualize them. So for random assigning of different spins to the nodes, a for loop is needed. The assignment of spins are random, therefore we need to use rand function in MATLAB. Rand function produces positive real numbers less than 1. Because we have also negative spins, we need to at first define a negative spin to a point. Then using an if statement, we decide about the sign of the spin. So here R&D variable is defined to see if it is necessary to change the sign of the spin or not. If R&D is positive, the spin is positive half. For drawing a honeycomb structure, a line function with 2 for loops are used. We want to draw a line between adjacent nodes to show the honeycomb structure. Therefore, an if statement is defined here. The distance of nodes are measured, and wherever this distance is less than 4 and longer than 1, there would be a line between corresponding nodes. Then for overwriting on the first image, the honeycomb structure, we need to use hold off and hold on codes. In this part, we need to add stems to show the spin of each node on the lattice. Up spins are red and down spins are blue. So there should be defined 2 stem 3 for each spin. The stem 3 is used for showing corresponding spin of each node. And That's a result of this part of this code, and it shows the result of the code, including the lattice and spins, up and down spins. As you see, the MATLAB override the spins as a stem on the lattice and does not start drawing new image. Thank you for listening, and please let me know if you have any question.
Okay, thank Payman. Do you keep your tradition of not asking questions, or someone wants to learn things? I also do not have questions because it's quite clear. Even if I want to do a provocative. Yeah, thank you, Payman. Let's once more. Any questions online? No. Okay, let's thank Payman once again.
You're welcome. Thank you.
So please stop sharing, and thank you to all previous speakers for being really great in matching the time. So for you,
I changed something around. So I'm gonna.
yeah, the only one is used for the camera.
Yeah. Okay.
Are we? I just wanted to check if you share screen. Share. There, so.
Hello, can everybody hear me? Online? Yay, no? Yes?
Yes.
Okay, perfect, thank you. So today I'm going to talk about Monte Carlo simulations, the Metropolis Hastings algorithm, and then how we utilize both of those for energy minimization. A really intuitive way I've actually, what? Oh, a really intuitive way on how to represent what a Monte Carlo simulation is if I have a robot that drops balls within this shaded rectangle here, it has three options. One, a ball can land in the sphere with the cross-section area pi times x squared. The ball can fall somewhere in the gray area and not be counted at all. Or the ball can fall into the box with the cross-section area of A is equal to x squared. And what a Monte Carlo simulation gets down to is it utilizes random numbers to approach some particular value. And one second, I need to just move that little window. What? Okay, let's just move it there. So what we can see is that since the cross-sectional area of the circle is pi times x squared, where the square is x squared, as we drop an infinite number of balls, the ratio between the number of balls in each container will approach pi. And so this is how we can use random numbers to approach some given value. And then the Metropolis Hastings algorithm utilizes random numbers to approach something we're looking for. Generically, we pick a arbitrary point on typically an unknown probability density. But the way I like to picture this is there is some function that defines our system, and we don't know what that function is. The best we can do is pick random points, calculate what the function value is, and then kind of adjust. So if I pick a number here, we can calculate the function value, and then depending on what we're kind of searching for, that's going to adjust what we're going to do. So in the case of our situation and the ruthenium chloride lattice, what we do is we kind of do a shotgun and assign spin states that Payman actually talked about, so I won't go too far into that. But we can calculate the energy of that conglomeration of spin states, and we just kind of define that as E for the microstate. And then what we do is we randomly flip one spin in the lattice, and we see how that affects energy. Because we are trying to minimize the energy of the system, if the energy, the E mic prime goes down, we accept that and then repeat the process for that new situation. So that's what the Metropolis Hastings algorithm is going to do. and we're going to utilize Monte Carlo simulation to do it. So the game plan: first, set the random spins, compute statistical sum and observables, and then we're going to save the observables and go back setting random spins. I won't talk too much about this because Payman did a much better job than I could. The first string here is setting the initial spins, and then we're going to see what effect that has on the total magnetization. And then we're going to calculate the energy of that microstate, which will be E mic without the prime. And we're going to use that by multiplying the spins by the Ising Hamiltonian that Sohi talked about, and then adjust that based on how it changes with the magnetization. Okay, so this is where it gets a little more complicated. We have to randomly select a ruthenium atom somewhere in the lattice. So correct me if I get this wrong, but I believe what we do, this function here picks a number of the ruthenium atom from 1 all the way up to the maximum value. So we really have a big spread on what we can do. And then the next line will flip its spin, and then you'll calculate a few things. You'll calculate the change of magnetization, and then you'll calculate the new energy called candidate energy by doing the same calculation we did on the previous slide. And then if this new energy is lower, because again, we're trying to minimize the energy of the microstates, then we accept it, and then we plug it back in to the previous step and then keep going. If it's not the same, then we plug our original value back in, flip a different spin, and then see what happens there. Oh no, I did the same thing. It's up, okay, thank you. And then finally, we have to start calculating our observables and logging things. So the first thing we're gonna do is calculate the energy of the new microstate, see how that affects the Boltzmann factor, and then see how our small changes, this end bit, we have to see how all of these small changes we just made affect the average of the observables. And then now that we're here, we can calculate the statistical sum. And then I'm not too sure why we need to calculate the root mean square, but we do that as well. And then finally, save those observables. I'm not 100% certain what this last bit does. I assume that every time we complete calculations, it goes back up and does them again. Are there any questions?
Let's thank speakers.
Thank you.
First, and now.
Oh, yes.
You can ask further questions. Excellent. And congratulations to the first question in the class.
Oh boy. No, it's a perfectly valid question. I'm really sorry I can't like even come up with anything for it. I would assume it makes further calculations for like heat capacity easier, but I wouldn't know why.
Okay, so let's try. There are two directions of thinking. First, that one can always say without thinking, because any system wants a minimum of energy. And it, to describe realistic system, one needs to find solution, right? No one will blame you if you say this, and it will be correct. Second, when here in class we were doing statistical sum, the partition function for two-level system. Which contribution of which state gives bigger contribution?
Lower energy state?
Yes. And if there are only two states and temperature is not big, what's the difference of this contributions to partition function? Are they like 10% and 90%, or they are like 1 and million?
Probably like 1 in a million.
Yes. So the contribution from the lowest state gives the vast majority of the whole partition function. So we do not have luxury to this.
Okay, so we need to calculate the minimum energy microstate because that's going to have the most effect.
Yes.
Okay,
for other states, you can toss these little balls into bucket. But for the ground state, you still need to find it for sure.
Yeah.
Yeah. Thank you, Sahir. Thank you, John. Any questions online? questions on line 1, questions on line 2, 3. No questions.
Thank you very much, everybody.
We need to stop sharing, and the next presenter is Crystal Grigor. So from finding minimum, she will teach us about scanning through microstates, and floor is yours. The virtual stage is yours.
Okay. So I'm going to talk about the 8th part, which is the cycling over the different microstates. So for mine, the command starts out where it again, like Payman had explained, we start out with the loop. And so, which I really appreciate like explained that, so I'm not going to repeat that. But anyway, so as Dr. Clean said, is we're going to start at loop 4 instead of 1 due to preliminary studies that they did earlier. And then line. And then way down on the end, this line 15, this corresponds back with the Isington Hamiltonian that was discussed earlier on today. But that's where it comes back up to play again. And so that dictates the energy of the microstate after calculating the Isington Hamiltonian. So after we calculate that, then we go back through and we find the energy of that new spin state, so the energy of the microstate. And then we have to calculate the Boltzmann factor, which is this W mic, using that energy over the KBT, just traditionally how to calculate the Boltzmann factor. And then when we come down to here, we get to update our value into the energy of the new value, so we can actually do that calculation. 333 right here, sorry. So this calculates our energy of our short ensembles. This is our new energy, which we calculate by taking our previous energy times that Boltzmann factor, which updates it, and then we can use that one to find our new percent magnetization. And so the main part though here is when we're saving these observables, we take our ensemble and then we set what our new lines for our ensemble are. We have loop, which indicates the number of the microstate, just like where we started off with n equals 4 earlier. So that'll set what the microstate number is. E mic is your energy. Your M mic, this is your energy of your magnetization. And then we have W mic, which will give our Boltzmann factor. Z mic, which is the updated part value of the partition function that we've been calculating by using that magnetization value times the magnetization value of the Boltzmann factor for the new one for the minimum. And then we have our average E mic, which is the expectation value of the energy. And so the states one that John was talking about, that was actually part of mine too. This actually is what generates the Monte Carlo method. And so here's like an image from Wikipedia. And so this is actually where I spent most of my time on looking into the Monte Carlo method. Was so you can take, it was actually named after a casino town in the old days because they figured gambling was a lot similar to the Monte Carlo method. And the dude that invented it was actually out sick. He had the flu, and so he was wondering, because there's a game of solitaire that's played in the casinos where you had to buy a deck of cards for some sites say 50, some say 52, and you lay them down on these like stacks that the dealer sets up, and then if you win, you would have got 500. But most of the time you lost. The casino ended up making lots of money that way, but because of the chance of winning, people would keep doing it. And so the dude, when he was sick, was like, well, I wonder what the probability is if I lay all these cards down, like what's my probability of actually winning? And so out of that came his idea, because he realizes that, well, he doesn't have to calculate every attempt, he just has to calculate them out of 100. And so then they realized that you'll still get that same distribution curve, and so he correlated that from when he was sick to like an actual like starting to create this Monte Carlo method. And so you drop a ball or a point. I was saying John's lingo. But you take this point, and so you set your exterior parameters of what you want it to be. So from like 0 to 1, 0 to 1, and then they showed how if you inscribe a fourth of a pi circle within that square, if you were to randomly put a point and just generate it, is you'll slowly be able to actually calculate pi just by random distribution of those points from where they actually fall. And so this one, when you watch it on like Wikipedia, goes from being this gray color to being fully saturated with points. And so the more points you give, the better it is. And so when you're going to do this generation, and that's why we go through this process of generating more and more points for this through this process, is so that we can actually create these points and get about the Bell distribution of, and then we can actually calculate our lowest point from there. And so in the end, once we've generated all of these points, then we plot them using this command ensemble for each, and then we save it. And so when I ran these commands, I got this bar graph for my part, or this line chart, I should say. And so what this shows is the magnetization value would be -16. Our absolute magnetization value, it'd be positive because, well, that's just the, and then the error, as you note, like each of them have like a little curve, so this ends up having like a triangle across, is the error incomplete in the magnetization. And then I was talking with Dr. Fleen, and he recommended that I test just the plot ensemble for the first two, which correlates to the energy of the system as we take more microstates into account using that Monte Carlo method. And so as you can see, when we just take a couple microstates into account, it's not very accurate, but as we take more and more and more microstates into account, it becomes fully pretty well parallel. So we actually can see that your average energy is pretty precise just by taking more and more microstates into account, because like here you're up to 2 times 10 to the 4th, so 2,000 microstates. And then after, just to kind of see how the energies effect was, average energy of function temperature, when I ran like the whole command, and then I typed this command plot equals -xj comma y, we can see how the energy of these microstates are impacted as the temperature increases. So yeah, so I guess overall, my part was looking at how using the Monte Carlo method to generate all of those microstates, and then how as those microstates become larger, we get a more smooth bell curve. And I guess with that, are there questions?
Join me thanking Crystal. Very, very strong and interesting. Any questions in the class? Any questions online? Can you please share screen once again and put a couple of slides to the middle? It will be not a question, it will be more a comment, but back once, but just put back. One more. Yeah, stop here. No, one forward. So this, if there will be 10 attendees of the class, this would be the presentation number 10, the meaning of the states function. So this, it's not a question to Crystal, it's only a comment for us to progress later. The file, the variable and file states accumulates all microstates explored in this loop, and later on saves to the file. So it shows number of microstate, energy of microstate, and then logarithm of this Boltzmann factor. So later on, it is not directly reflected in observables that we are going to predict, but it helps to interpret, especially to answer question of Sophie to John, because it will, one can plot it versus make plot with energy on the x and make number of microstates along on the y. So I think it is what you got in the first part of the class. So for each system that one tries to describe statistically, one needs density of states, and then one practices Boltzmann factors. So it would be a connection and interpretation. Questions right now, maybe for when we will be doing presentations next time, I'll try to distribute all slides to everyone and ask to prepare questions at home, right? Because now we are under stress of the short time. Okay, many thanks. Please join in thanking Christian. I saw how people on the talent show are applauding when your friend is busy with the and the next presenter is Ichi Chan. They pronounce well.
Hello everyone, my name is Ichiu Qian, and I will introduce the last part, which is calculate heat capacity from the here's what we get from energy. So what we said right here is the x-axis is the temperature and y is the energy from our previous data. So we try to get like less noisy data from the energy first. So that's the reason why we do the average of y I minus 6, which is whole divided by 13 what we get. And the specific heat 1 is what we do for like derivative of the y, which is the energy, and over our delta temperature. So from the definition, we know our heat capacity is the derivative of energy over the temperatures. And but the problem is we don't have the 0.0 energy of our delivery rate. So we gave the specific heat 2, which have one more 0 point to our data sets of the specific heat 1. And then later on, we do the plot again, and I will show the figure later, and which show the relationship between our 0 and delivery rate of our energy temperature relationship. So based on that, we also do another smooth, and we save that data, and then we do another reference lines, which we know we do the different delivery rate of tangent 8, tangent H temperature status, which is what we get from our equation of our last homework. And then we plot the line into our figures. And we give the name of our labels by temperature for the x-axis, of temperature to spring-spring coupling ratio T over Z, and also our y labels as specific heat. So this is the figure what I got. The blue one is the data we get from the delivery rate of our energies, and the red line is the reference line of directly get from our equations. And that's all I have. Any questions?
Any questions in the class? Any questions online? I do have a question that we could either speaker or we all together answer. Can you please go to the first slide? Yes. So this one sets y as spline of y, right? takes an average over near one neighbor. But what is function y? What is variable y? Anyone is welcome to help. I believe that Crystal may answer it at a short span. So anyone please try to answer what is y, single y, not triple y, but single y.
The single y, is it average energy?
Yes. And right, everyone agrees. And where this energy is taken
From purest data.
Yeah, from not in a philosophical sense how it is computed, but mechanically from which variable it is taken. Crystal, would you like to comment?
You just mean because it's the energy of the state, microstate.
No, average energy. Average energy.
Of the system? Yeah.
Let me bring slides So the y variable that you are plotting and using to compute heat capacity, it comes from this one. So in the ensemble variable, it is 1, 2, 3, 4, 5, 6, right? And if we go to the next slide, yes, if you go to the slide that Crystal was trying to show to all of us, so if one, instead of redesigning variables, she was just plotting the element 6 of this variable, which is average energy at a given temperature. So this is so here it shows at the end of the ensemble, but for given temperature we need only the last value, right? So we do the whole ensemble, find this average energy, and then we save it at each temperature, and then it is what Ichi was using to find the heat capacity. Make sense?
Yeah.
Whew. I know it was not quite like questions and answer, but I think if you all are on the same page, it's good. Any other questions to the speaker? No. Okay. Thank you, Ichi, and all speakers for nice presentations. So everyone gets sufficient credit towards getting maximal grade at the end of the semester. This presentation is counted as midterm number 1, which you have successfully passed with great success. And see you on Wednesday in the computer lab.
Thank you.
Thank you. Any just questions online? We have everyone is welcome to depart and disconnect. Just checking if any discussion points come up.
No.
Okay, then I'm going to disconnect, and I will share maybe by midnight the recordings.
Thank you.
Thank you.